Hello everyone, welcome to video 19. The topic for this video is going to finish out kind of the part 2 of conic sections, which is going to be over hyperbolas. Now the lesson objectives, as you can see here on the screen, is going to be, we saw that ellipses was the set of all points whose total distance to the two focal points was always equal. But what if, instead of adding those two distances, what if we ended up subtracting those distances? In other words, what if we try to maintain that difference also remained equal? What would happen to the graph? And what kind of shape would we essentially get? And so this is actually the core definition for what's known as a hyperbola. Now, a hyperbola, if you kind of look almost kind of at the root word of this, it's very similar to parabola. You can kind of notice the bolus at the end, but this is a hyperb below, so a hyper. And the reason why it's essentially called that is you're going to see when we graph these next three examples here that it's going to be essentially two parabolas, both opening in opposite directions. They'll either open vertically, so you'll see them open along a vertical line, or they'll open along a horizontal line. And so hyperbola is specifically defined as the creation, or is created by the set of all points where the difference of the distances from the two fixed points, which we again call foci, to the curve remains constant. So this means that any point you choose on the curve itself, if you were to draw a straight path to each focal point, the difference between those would always be the same no matter what other point you picked on the curve and did the same process. So it always remains constant to that focal point. To the difference remains constant of those two different focal points. All right, and so kind of like what we did with ellipses, I want to kind of go through and we're going to graph these three examples here in Desmos. And the goal here is just to kind of say, okay, well, how are the equations similar and how are they different? And then how is the graph related to the equation itself? So what can the equation tell me about what the graph does, what it looks like? So then we can take that and apply it to a more general equation and general process. And so as of right now, I just kind of noticed that one of the big similarities and one of the big differences from when we did ellipses in the previous video is that for hyperbolas, there is a subtraction here. And what's nice about that is notice the direct correlation between the minus in the equation and the definition for a hyperbola, which is built around this idea of a difference. So there's, again, kind of a connection there. The next thing to kind of notice is that for the graph of A, it's going to start with x squared minus a y squared, versus in B, it has a y minus an x. So you can kind of see the order. So we'll kind of look at how that plays a role. C goes right back into that. We'll also kind of see like what's the difference between, again, the number underneath x being larger, the number underneath y being larger, and then again back to looking at one like this. So I'm going to open up Desmos on this video. I would encourage you to actually try this first on your own and then go through and kind of play with these graphs. But I will kind of walk through and talk about these. So I'm just going to go and open up Desmos. And so you'll see I've got the graphs there on the left-hand side. I'm going to go in kind of projector mode. And let's graph the first one. So in the first function, notice that there's no h and k. Like when we did circles and ellipses. So my guess is that the center would be at the point 0, 0. And if you notice that this graph with the x squared coming first, see how the hyperbola is opening horizontally? So it's opening along the x-axis. And so it's opening to the left and right. The next thing to kind of notice that in the equation for this, underneath the x squared was a 100. And if we look at where these vertices are, so where these two parabolas here, these two pieces kind of hit that horizontal line that the center is on, is 10 steps away from the center, or the square root of 100. And so we can then kind of predict and take a stab at that, just like with ellipses, the square roots of the denominators, specifically to x and y, will correspond to the distance from the center to those points. And so when the x squared is listed first, this is telling me and describing how it's going to open, but it also tells me exactly where the vertices are and how far away they are from the center, again being 10 steps. Now, one of the biggest differences here is now that underneath the y, this b, which I'm going to highlight here, being 4, notice there is no vertical steps up or down. And that's the part that's going to be kind of interesting here, is that unlike with ellipses, there is no co-vertices here for hyperbolas. So what's going to happen and what will play a role here is actually kind of a characteristic for hyperbolas. And we're going to see this characteristic by essentially zooming out. So in other words, if I kind of go out further and further and further, what's going to happen is those vertices are essentially going to look like they're combining into the middle, and my graph loses its curvature, and so the graph begins to look like a giant X, right? It looks like two lines, one line that is increasing and one line that is decreasing. And we could go through and essentially kind of predict what the slopes are here, and we could write an equation for it. Instead, what I'm going to do is I'm going to kind of zoom back in and kind of go back to the original graph here. And I'm going to plug in this for my vertical, or for my asymptotes, not vertical, sorry. Y is equal to, and I'm going to choose to do 4 divided by 10x. And you'll notice the 4 and 10 there are not just random numbers that I chose. I chose those very specific to the equation that we're graphing here for the hyperbola. 4 is b, 10 was a, right? The square roots underneath the x squared and y squared respectively. And so when I take this to be my slope, this b over a, if I do the negative as well for b over a, it's going to give me the other side of it. And so these are my asymptotes for hyperbolas. You'll notice the curve will always stay within these guidelines. And as we get further and further out, the curve will continue to approach these vertical asymptotes until we're so far zoomed out that it appears it is those asymptotes. It's just gotten so close that we can't distinguish between the two anymore. And that's the idea, remember, of asymptotic behavior, is that the curve will get closer and closer and closer, but just never touch when we zoom far enough out. It will describe the behavior. So hyperbolas have asymptotes, and that's one thing that we're going to have to find. But what's really nice about it, again, is it's determined by the relationship between b and a, specifically that the slope is b over a. All right, and so here's just kind of everything with the first equation. So let's go through and let's see if we can kind of take a stab at what the second equation would do. So I'm going to kind of turn those off. So just looking at the second equation here, if I had to take a guess at where the center would be, if it's similar to how an ellipse works, I would say that my h, which is in there with the x, would be -6, and then my k would just be +2. So my guess is that the center would be at -6, 2. So let's go ahead and graph this, and you'll see that that sits directly along the vertical. So I'll kind of put in a vertical line there at -6. Excuse me. And so you'll see that the graph opens along this vertical line. Notice how the y squared term comes first. Because we're doing subtraction again, the order is really going to matter here. And so what determines for a hyperbola if it's going to open up and down versus right and left is which comes first, x or y, right? X always normally represents horizontal, y always generally represents vertical. And so that's a really big context clue in the equation. So then if we're looking at in terms of going up and down, then notice that the vertices here, these intersection points where these hyperbolas meet, are exactly 7 steps above and 7 steps below where my center value is at -6, 2. And 7 is not just some random number again, but it's the square root of 49. So then if I was to take a guess at what my what my asymptotes are for this problem, again, if I take my b over a here, so my b again was 7, my a this time would be the square root of 36, and then I do the same thing here, 7 over 6, and graph these. Notice that this is all centered around at the origin, because when we wrote these originally for the previous problem, there was no shift, right? The center was at the origin. So I need to apply the shifts that were applied to this function to move and relocate the center. Well, that shift was specifically -2 to the y, and then on the x, it was +6. And so this is how we can do a transformation and adjust for each hyperbola and each shift. And so now notice this point right here will go straight through the center, and now my asymptotes better correspond to the graph of my hyperbola. All right, and so this is some information that we could tell again from it. All right, so if we did the same idea again, this time focusing on the third one, my prediction would be that this graph would open up left and right. So in other words, that middle axis is going to be horizontal, so it's going to open along that. Here, my h is 1, comma k is -7, so this is where I'm going to predict my center to be. So it's down there. Kind of zoom in a little bit. All right, the next prediction again is that it's going to open right and left along the horizontal, so that would be the horizontal at -7. So I'll kind of put that in here so we can see it. And then let's go ahead and graph it. So I'm just going to kind of plot that in, and then I'll kind of zoom out a little bit so we can see it. If you look at the intersection right here where the vertices are, notice how that's going to be exactly 3 steps to the left and 3 steps to the right. That's what's underneath the x there, 9, right? So the square root of 9 is 3. And then if I want to go through and figure out what the asymptotes would be, again, I'm doing that based off of b over a. So in this problem, that would be 2 over 3, and then -2 over 3. And although I've gone through and I've changed the slopes, I need to also apply the same shifts. So how this problem is x minus 1, I need to make this x minus 1. And where it's y plus 7, I need to make this y plus 7. Graph that. There we go. You'll see it go through our center and better fit our data. Do the same thing, x minus 1, and then y plus 7. So you can see that the asymptotes are essentially just doing whatever these parentheses are in the original format. You're just putting them in for x and y. But that's how we graph hyperbolas. I'll show you kind of a better, or at least how they also relate to the equation. And I'll show you a little bit more by hand, getting back into the lesson and writing out like the equations and give you some more terminology to this. All right, so let's go back into my notes app. I'm going to pop my laptop down. All right, and just kind of scroll down. And so we can kind of take a look at the equation of a hyperbola. All right, and specifically just kind of starting with just the characteristics. And these are the characteristics that we went through and just saw through those 3 examples. That the center is going to be located at h comma k. The vertices are always located on what's known as the transverse axis, and the foci are also located along that transverse axis. When I was referring to how the hyperbolas were opening to the left and right along that line, that horizontal line, that line is referred to as the transverse axis. So that's what it's actually formally called. And you'll see that here as this represented as this blue line for this graph that's opening to the left and right. If my graph is opening up and down, the transverse axis is vertical, and then it would open up along that line. Now the line that is perpendicular to the transverse is called the conjugate. So again, this just depends on how I'm opening. So again, if this graph is opening up and down, then the conjugate axis would be horizontal. If this graph is opening to the left and right, the conjugate is vertical. So our conjugate just means reverse. So hopefully that kind of helps with that. Like we talked about a second ago, the asymptotes for a hyperbola will have the slope plus or minus b over a, and then it is given by the formula here that we saw earlier. Now you'll kind of notice in the picture, and this is why I think drawing hyperbolas is kind of fun, that when you have your center, notice that there is a box created by walking up b and down negative b, and then going out a and negative a from your center. And then the asymptotes are created by connecting the diagonals of that rectangle. And that's why essentially the slopes are always b over a, because that's my rise over run to get to the corner of the box. And so this is a property of hyperbolas. All right, is that this is how the asymptotes are actually created, is that it's by drawing a box that essentially has a length of double A, right? It's a distance of A, and a height of double B. And so again, walking from the center, we get B over A, and that'll kind of give me that main diagonal there. Just like with ellipses, we can talk about the eccentricity, which is calculated by C over A, just like with hyperbolas. Eccentricity is just defining the curve, the curvature, the roundness of the hyperbola. And formally, C again represents the distance from the center to the foci. So if I'm here at the center, if I walk C to the right, that's going to get me to my one focus. C to the left is going to get me to my other focus. And for hyperbolas, it's very, very easy to remember because it's specifically Pythagorean if you think about the variables and the letters that we used for that. In this situation here, c squared is equal to a squared plus b squared. So that's how we can actually find the distance to my foci. So let's consider a new hyperbola, something that's kind of similar to what we did before. And let's go through and sketch it. And then let's label where these points are. And then we'll kind of, I'll give you or formally define the actual equation, like the general equation that you'll need to be able to work it with. So the first thing I'm going to do here, every time I look at a hyperbola, is I'm going to essentially recognize which term comes first. So because x comes first here, this means that my transverse axis is horizontal. So this graph is going to open to the left and right. The next thing I'm going to do is go through and notice that, okay, well, a squared is equal to 9. So therefore, a is plus or minus 3. B squared is equal to 16. So that means B is equal to plus or minus 4. The center, there is no H and K here, so it's understood to be 0, 0. And at this point, I can actually go ahead and go to my graph and begin to draw approximately what this hyperbola would look like. And that's the other really nice thing about hyperbolas. Other than locating the foci right now and the asymptotes, we can actually get a really good sense of what this looks like immediately just from these two, really these 4 pieces of information. So I know my center here is at 0, 0. I'm opening to the left and right, so I'm going to walk out A. So that's 1, 2, 3. I'm going to put my dot here. And then 1, 2, 3. Here's my other dot. These are my vertices, so I'm going to mark these with a blue circle. All right, and then I'm going to walk B up, so up 4. 1, 2, 3, 4. And then down 4. This is essentially allowing me to create my box for this hyperbola. And it will allow me to draw out what the asymptotes look like. That will then give me the boundary for what my curve will do. So given this box now, I can draw my asymptotes by drawing the diagonal through the center. Now to go the other direction. Kind of missed that corner, but it's okay. All right, and then I can actually draw now what the parabola, or excuse me, the hyperbola is by opening along these asymptotes. Now, because of the scale of this, obviously it's going to look really, really wide. That's also true because if I go through and find the slopes of my asymptotes, the slope is going to be plus or minus b over a, so it's going to be 4 over 3. And the formula will be y is equal to plus or minus 4 over 3 x. That'll give me both of those equations. All right, we've located my vertices. We've got the equations of the asymptotes. So the last thing that we can really do here is find the focal points. We can find my foci and then plot them and label them. And so my foci, remember, the equation is very similar to Pythagorean. It's that c squared is equal to a squared plus b squared. So in this case, we know both of those as 9 and 16 respectively. So I get c squared is equal to 25, which tells me c is equal to 5, specifically plus or minus. And so this will tell me that to get to my focal points, I need to walk 5 steps to the right. So 1, 2, 3, 4, 5. And 5 steps to the left. 1, 2, 3, 4, 5. And I have one focal point here, so I'll just call it 1. And there's the other one labeled. All right, so that kind of completes example 1. It also kind of gives you a really good general overview of how we're going to graph these ellipses. Hyperbolas. All right, so let's take a look then at the equation for a hyperbola. So here's the equation written out, x minus h squared over a squared minus y minus k squared over b squared. In this kind of example, again, the center would be notated at hk with the transverse axis horizontal because the x term comes first. The asymptotes are always given by plus or minus b over a, which means then y minus k is equal to b over a. The foci, c squared is equal to a squared plus b squared, where c is the distance from the center to the focus, and the focus lies on that transverse axis. So then the only thing that we really have to take into account is that if the x and y terms are swapped, so if the y term comes first, we just need to recognize then that the transverse axis is vertical, and then I need to take my steps up b, and then again it's b over a in terms of calculating the slopes. Now, the way that I've gotten this written is very different if you were just to Google hyperbolas and the equations for hyperbolas. So if you're going to use my formulas and my reasoning here and what I do throughout this video, try to be consistent. Otherwise, you will confuse yourself because they kind of swap the A's and B's. I think it adds too much complexity. I just like to keep it simple. A is always underneath X, B is always underneath Y. And then the only thing you really have to take into account is this. To me, it's just much easier. So that's the way that I kind of teach it. So just be aware of that. Again, if you're just kind of randomly Googling, using somebody else for help, or again, using some other textbook, whatever, than what I'm essentially showing you. All right, so let's take a look at example 2. And this is really the end of this lesson. It's a fairly quick lesson because after running through how to graph these, that's really it in terms of what we're going to do. The next step then is like we did with circles and ellipses, is that a lot of the time my formulas aren't written in graphing form. So what we need to do is rewrite them into graphing form by completing the square, and then go through and we're going to state the vertices, the asymptotes, and the foci. So I'm kind of making all this stuff kind of flow into this one ultimate problem so you can kind of see how everything's done. Again, feel free to kind of skip through as you need to. I'm going to walk through every single piece here, which will make the video a little bit longer, but you can kind of see what my reasoning is and kind of hear as I kind of talk through the problem. So I just want to make you aware of that as we get into it, but feel free to kind of skip around as necessary. All right, so example 2. So we need to rewrite. So let's look at part A here. And I need to rewrite 4x squared minus 9y squared is equal to 36. Now, when we're going to complete the square here, I need to get it equal to 1. Now, what's really nice about this one is that they're already factored, right? There's no other x terms, no other y terms. So essentially what this problem looks like is x minus 0 squared minus 9, y minus 0 squared is equal to 36. So I can immediately divide by 36 and get x minus 0 squared over 9 minus y minus 0 squared over 4 is equal to 1. So now I have this in graphing form. And so notice that the x term comes first. So this means that the transverse axis is horizontal. So this graph is going to open to the right and left. My center, I've kind of written it trivially here where I've kind of given you the h and the k as 0, 0. So this is going to be at the origin. So this means to find my vertices, I need to know what my a is. So a squared here is equal to 9. So then a is equal to plus or minus 3, kind of like what we saw before. But probably the biggest difference between this and the previous example is that b squared is equal to 4. So b is equal to plus or minus 2. In other words, notice how we're taking more steps to the right and left than we are up and down. So this hyperbola is going to be a little bit more squashed in terms of what it looks like than what we saw previously. All right, and so with this information, I'm just going to go ahead and make a sketch of this hyperbola. As I'm drawing this, I actually started making this video the day before, and this was about the time when my screen recording quit on me, so I'm kind of nervous. Hopefully it doesn't quit on me, so I don't have to redo this entire video. So fingers crossed, everybody. All right, so there's my center. To get to my vertices again, I'm going to take 3 steps to the right. So 1, 2, 3. There's one vertex, I guess. 3 steps to the left. There's my other vertex. So here are my vertices. And then to create my box, remember we're going to take steps for B. So up 2, there's the height. Down 2, there's the depth. And then I'm going to make my rectangular box here because I need to draw out my asymptotes so I can see the overall parabola shape. So I'm going to kind of I'm going to sketch through and draw my diagonals. So there's 1. Here is 2. We'll find the equations for these in a minute. So you can kind of already tell how this is going to be a little bit more squashed. All right, and then I'm going to go ahead and draw my curves so they fit within this. And you can over-exaggerate them a little bit if you want to, especially if you're doing this by hand. You can then graph this in Desmos to kind of double check our work and kind of make sure that we've got everything kind of located right. Now the next thing is to go through and find the equation for these asymptotes. So I'm always going to start by finding the slope first. So the slope, remember, is plus or minus b over a. So in this case, it'd be 2 over 3. And then the equation is found by doing y minus k, so y minus 0 is equal to plus or minus 2 over 3, x minus 0, or just x. So there's the equations for my asymptotes. So then the last thing that I need to kind of locate and find here are the foci, and then I need to plot them. So the foci, remember, is c squared is equal to a squared plus b squared. So very similar to Pythagorean. A squared was, again, 9. B squared is 4. Make your life easy. They tell us that, remember. And so then I get c squared is equal to 13, or c is plus or minus root 13. What I like to do with this, because I'm just going to essentially approximate, is that, again, 3 squared is 9, 4 squared is 16. So this answer sits somewhere between 3 and 4. And then because it's 13 is roughly in the middle between those two squares, then my guess is that it's going to be roughly in the middle between 3 and 4. So I'm going to say this is roughly about 3.5 is the steps that it's going to take to get to my focal points from the center. So I'm going to kind of take 3.5 steps. So 1, 2, 3.5. So one focal point here, and then 1, 2, 3.5. So one focal point here. Now, if I wanted to find the exact location, I'm adding root 13 to 0. So root 13 comma 0 is that first one, and then negative root 13 comma 0 would be the other one if I'm looking for those ordered pairs. All right, so that's A. All right, so for B, I've got 4x squared minus 24x minus 25y squared is equal to 64. So for this one, I need to actually group up because I have two x terms. All right, so I'm going to group up my 4x squared minus 24x. Minus 25y squared is equal to 64. And then from that first parentheses, I need to factor out a 4. So I get x squared minus 6x. I'm going to leave a space for my missing term here. Minus 25y squared is equal to 64. All right, and so now when we complete the square, remember, I'm going to take this middle term here and divide it by 2. So I'm going to get negative 3. And then that gets squared because, again, we're completing the square. So I need to add 9 here in order for this to factor. All right, and so then when I add that 9, though, I can't just add a number randomly. Remember, we need to go through and balance that by adding the correct value on the other side of the equal sign. And this is where, again, I'm not just adding 9, but I'm adding 4 times 9 because of the multiplier. So I'm really adding 36. So I need to make sure that's what I put on the other side. So that way now I can go through and actually factor. This would be x minus 3 squared minus 25y squared is equal to 100. And it's really important that these are the values we get, and hopefully you're kind of picking up on the pattern, because whatever I divide by needs to cancel out those coefficients out front, those scalars. And so the next step here is to divide by 100, like I was just talking about. So this would give me x minus 3 squared all over 25 minus y squared over 4 is equal to 1. Here's my graphing form. Okay, so from this, we can see that the x term comes first. So this means that my transverse is horizontal. Excuse me. The center is located at 3, 0. So that means when I find my a, so in this case, a squared, here, I'll leave some space. A squared is equal to 25. This is telling me that a is equal to plus or minus 5. This gives me the steps to my vertices since I'm moving horizontal. For my b, I get b squared is equal to 4, aka b is equal to plus or minus 2. So this tells me that my asymptotes, I can just go ahead and find those now. The slope will be equal to plus or minus b over a, so 2 over 5. And then the equation would be given as y minus 0, since there's no vertical shifts for the center there. My slope, which is plus or minus 2/5, and then x minus 3, since that's the shift with my center. And so here, I'm going to go ahead and graph it just got my notes open with me so I can kind of see, make sure I leave myself enough space. All right, so I'm gonna go ahead and graph this. So let's put it, I'll need a decent amount of space. Let's put it right here. And I may move this stuff over a little bit. Excuse me. Okay. My center again is at 3, 0, so 1, 2, 3, so that's right here. My vertices, I'm taking 5 steps to the left and right, so 1, 2, 3, 4, 5. Again, remember these steps are taken from the center at 3, 0. So you'll notice that I've got one vertice at, I'll write it up here. I've got one vertex at 8, 0, and one at -2, 0. That's adding 5 and subtracting 5 from H. All right, so I've got that. We could go ahead and make the box. So from the center, I'm taking 2 steps up. Again, this is going to be a really shallow box. And then I can create my AA by BB rectangle. This will help me draw my asymptotes, because my asymptotes will go along the diagonal here. This is why I needed a little bit more space. There's that one. A little extra line, maybe a little off, but that's okay. That. And then we can draw in what the hyperbola looks like here and here. So the remaining thing that we need to find are my focal points. Again, the focal points, same kind of, or the foci, same kind of thing. C squared is equal to A squared plus B squared. So I'm just going to go ahead and write that as 25 plus 4, or 29. So this means that C is plus or minus root 29. So you'll see a lot of times with these, other than hyperbolas, the math is going to be generally leaving you with square roots. So we're going to have to kind of approximate where we put these. They won't be at exact locations. And so plus or minus root 29. This is going to be a little bit more than 5, since 5 squared is 25. So this is going to be just past where my vertices are. And so I'm going to kind of locate them right here, just kind of approximating. And if I wanted to list their ordered pairs, I would list it by saying 3 plus root 29, again, 3 being that x coordinate of the center, and then 3 minus root 29, 0. There are the locations there for the focal points, the foci. Okay, so let's move on down to C now. 2 left and we're almost done. Excuse me. So for this one, I'm going to take a sip of coffee real fast. All right, and let's go through and group these. I've got multiple x's and multiple y's, so I'm going to kind of group them together. It's going to be my first step here. Plus 3y squared plus 36y is equal to 18. Now here in the first parenthesis, I want my first term to be positive, so I know I'm going to be factoring out a negative. I'm also going to be factoring out a 2, because that's the only GCF I have here between these two x terms. So then this changes to x squared minus 6x, and I'm going to leave an empty space there. Then plus, over here I'm factoring out a 3. Like so. Now, excuse me. Now here I want to complete the square. So dividing this term by 2 and squaring it, like we've seen already, this is going to be plus 9. But because my factor out front is a -2, I'm really dealing with -18. That's what I'm going to put on the other side. Then for the y's, dividing 12 by 2 is 6 and squaring is 36. I'm really going to be adding 3 times that, which is 108. And when I go through and factor, I'm actually going to write it so it's subtraction in the middle. So notice, because it's negative with the x's, that means the y's come first. So this will be 3y plus 6 squared minus 2x minus 3 squared. And again, I want to write it this way so I can see how the transverse axis would be. And so you always want to, again, I would encourage you to list the positive one first. Now, dividing by 108, this will get me to my final graphing form. 3 over 108 simplifies down to 36 on the bottom. And then this would come down to x minus 3 squared. This would be 54. This would all be equal to 1. So here's my graphing form. So then the transverse in this problem is going to be vertical. So my center, which is located at 3 comma negative 6, b, that square root underneath the y term, will determine where my vertices are. So just to kind of follow and maintain the same order, a squared is equal to 54. So that means a is equal to plus or minus the square root of 54. Now, if you're going to simplify and reduce this, 54 is broken down into 9 times 6. Square root of 9 is 3. The 6 stays. So that's how we can kind of simplify it. For b, 36 is a perfect square, so I get b is equal to plus or minus 6. My asymptotes, the slopes, are still going to be at plus or minus b over a. So this is going to be 6 over root 54, or 3 root 6. So I can simplify this down a little bit more by saying 2 over root 6. And I'll leave that for now. So then my equation, would look something like this. Y is equal to, y plus 6 is equal to my slope, which is plus or minus 2 over root 6. And then here, x minus 3. I know this is getting kind of clustered, so hopefully this is okay right there and seeing that. All right, so then taking that, we can go through and let's go ahead and create a sketch. Now, the sketch, again, hopefully I'm going to have enough space for this. I think what I'm going to do is kind of add a page underneath. Okay, so we've got a blank page. So I'm going to kind of use this down here because this graph is very tall. Okay, so here are my axis points. Now the center again was located at. Let me scroll back up here. Oh wait, no, there it is. The center is at 3, negative 6. So 1, 2, 3, and then going down 6. So 1, 2, 3, 4, 5, 6. Here is my center right here. Now I know my vertices are located by my b value this time, so this would be up 6. So that's going to put me back at the x-axis, and then down 6. So 1, 2, 3, 4, 5, 6. Here's the other vertice, essentially going down all the way down to negative 12. And then walking out my a, this is going to measure out my box to the right and left, which again is plus or minus 3 root 6. This is approximately, you can do this in a calculator just to kind of get a guess. 1, 2, 3, 4, 5, 6, 7. So it's roughly about 7 steps to the right and left. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Just to give a rough idea. And so then I'm going to draw this out. Oop, too far. Draw this out. So my corner is right here for when I'm ready to draw my diagonals. And I go down. Okay, so now I can go through and draw my asymptotes, which we have the equations for. This is going to be a very wide hyperbola. Now I'm going to go through and draw. So I know it's going to open up like that and open down. Transverse is vertical. And then we need to go through and find my focal points. So my focal points, again, c squared plus a squared, or excuse me, c squared is equal to a squared plus b squared, which in this problem is 54 plus 36. I'll do it in the right order. So I get c squared is equal to 90. So c is plus or minus square root of 90, which is plus or minus 3 root 10, since that's 9 times 10, and the square root of 9 is 3. So that, if we were measuring it, would come out to be roughly about 9 units, a little bit shy of 9. So walking from the center up and down, about 9 units. So that's 3 more from my vertice, 3 down from my vertice. There are my focal points. And if I wanted to write the equation for these, if I want to write the order pairs, I would say 3, and then I would say negative 6 plus 3 root 10. And then I would say 3 negative 6 minus 3 root 10. Because I'm moving vertically, so the x coordinate for the center, would stay the same for my focal points. Same thing if I wanted to list out the order pair for my vertices. So there's C. So let's take a look at D. I created a new page, so I've got D down here. All right, and so D is going to be kind of the ultimate problem a little bit. Everything kind of culminates up to the last one, but it's fairly straightforward. So let's go through and kind of do the grouping again. So I've got 4x squared minus 8x plus, and then I'm going to show the entire grouping there, minus 5y squared minus 30y. And I'm going to go ahead and add the 121 over, because I know I'm going to need to get that to the other side. Let's factor out the GCF. So I'm going to factor out a 4. So x squared minus 2x, leave some empty space. Factor out the negative 5. So this would be a y squared plus 6y with some empty space there. And then now let's go through and complete the square. So dividing negative 2 by 2, I would get 1, negative 1. Squared, though, is positive 1, which means I'm going to add 4 to the other side. And then from the y's, we've done this one plenty of times. I'm going to add 9, but I'm really subtracting 45. And again, that stems from the minus 5 here, and the plus 9 that I'm adding in. Okay, so going through and factoring and simplifying the right-hand side, this would give me x minus 1 squared minus 5, y plus 3 squared is equal to 80. And now dividing everything by 80, I get x minus 1 squared over 20 minus y plus 3 squared over 16 is equal to 1. Because the x term comes first here in the subtraction, the transverse is horizontal. So that means with the center being at h comma k, and this problem being 1, negative 3, I will be taking using my a value to get to my vertices. So a squared is 20, giving me a is plus or minus the square root of 20, which is plus or minus 2 root 5. 4 times 5 is 20. For my b, to help make the box, b squared would be equal to 16. B is equal to plus or minus 4. So then using these values, I have my asymptote has a slope of plus or minus b over a, so 4 over 2 root 5. I can simplify it down to 2 over root 5, plus or minus. And the equation then can be given by y plus 3, my slope, 2 over root 5, and then x minus 1, that shift there. So here it gives me both the positive and minus for my asymptotes. So at this point, we can actually go ahead and sketch it. So let's go ahead and make the graph for this. I'm going to go ahead and draw. Here's my y-axis. The center, again, is 1, negative 3. So I'm going to put the x-axis here, kind of just extend it, just kind of exaggerate it. So let's put it in the center. So 1, negative 3. So 1, 2, 3. So here's the center. Again, the transverse is horizontal, so I'm going to walk out my a. So 2 root 5 is roughly about 1, 2, 3, 4 steps, roughly. So I'm just going to kind of approximate it. So 1, 2, 3, 4, just for the sake of the video. 1, 2, 3, 4 to the left. So here are my vertices. And then I'm going to step B, which is definitely more exact, to get the top of my box, which is 4 steps. 1, 2, 3, 4. And then 1, 2, 3, 4. So this is pretty squarish. in terms of my rectangle and in terms of what the shape of the hyperbola would look like. So sketching out this box here now. I can draw my asymptotes. These would correspond to the equations we just wrote. One, there's two. And to find my focal points, c squared is equal to a squared plus b squared. So I get c squared is equal to 20 plus 16, which is 36. So c is plus or minus 6. So I can take the exact 6 steps here, and there are my focal points, and here's the graph of my hyperbola. All right, so that finishes out the final example here. So in closure, what I really kind of want to point out again is just the connection between hyperbolas and ellipses. That can be kind of interesting. So I'm going to go back to really the very first example today by turning back to Desmos and really kind of looking back at this original hyperbola here. And what I'm going to try to do, because I'm doing this kind of off the cuff, is I'm going to put in the box that essentially, remember, creates my asymptotes. So this one would occur, I'd have my top one at y is equal to 4, but again, this would only need to run from negative 10 to 10. So there's that first top half. The bottom half would be at negative 4, and then would run from the same thing, negative 10 to 10. The edges of my box are determined by the verticals at the asymptotes, so that would be at x is equal to 10. This again would only run from negative 4 to 4. So don't worry too much about having to create this. I'm really just kind of getting the lines in. The other one being at negative 10, negative 4 to positive 4. So here's my box. Let's make it all the same color. So let's do green, 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 and then we'll dot them. So you can kind of match what we did before. Okay, so here's the box that we would create, and then the asymptotes would branch off of that. Now, what's actually really, really interesting here in terms of the hyperbola and an ellipse is that the ellipse equation, if I was to do a very similar problem, all it would change is the plus sign. And so what I want you to notice is that when I do this, notice what fits perfectly inside that rectangular box. Right? It's the ellipse that would be drawn. And so when we talk about a hyperbola, one way that I like to really kind of look at it is it's almost like taking what this ellipse would be, the same equation, cutting it along the y-axis in this case, that vertical, and then essentially reversing those two halves, the left and right half side, and flipping it over. And you'll notice it essentially matches. The idea is that it just continues to open because it's never going to come back to the middle because of how we cut it. All right, but this is actually the connection between the ellipse and a hyperbola, is that I look at it almost like a swinging gate. But that box, what it represents is that the boundaries for my ellipse. And then by doing the subtraction, it's what then creates the hyperbola. So there's some interesting geometric properties and connections here and relationships. All right, and so that's it for conic sections. That's it for hyperbolas. Make sure that if you're going to do one of the project assessments, you choose one of the 3 options. Each option is a little bit different. The first option, again, is going to be going through and actually physically creating the sections by taking some kind of cone and cutting it. So if you're big into kind of arts, a little bit more artsy stuff, you can go down that route if you'd like to. You can create using clay, Play-Doh, whatever. The second option is going to be more mathematical. So if you're a little bit more mathy, go through and try that one. You're going to actually be coming up with the general equations. So it can be a little difficult. So let me know if you need to have any questions on that. And then the third option is to look around your house and see if you can find a conic section, be it an ellipse, a circle, or hyperbola, hopefully one of each, all 3. I'll probably require at least 2. And then taking a picture, putting it into Desmos, and essentially trying to come up with the equation that would model that. One example will be posted. If you ever look at a lamp with a shade over it, and if it's up near against a wall, the light will create on the wall the shape of a hyperbola with the shadow. So it's actually kind of interesting. And so that's one approach that you could do. And I'll show that essentially kind of as an example. So that's it. Thank y'all for watching. Let me know if you have any questions.